Alright, how are we doing? Welcome to this is your night before revision video. I'm just going to go through a whole bunch of bits and bobs of things that I think are really important for you to remember. These are some kind of set explains that come up time and time again, and I've asked you earlier just for your kind of key questions that you wanted, so I'm going to go through some of those as well. It's basically all stuff on space. If I had a answer already from just like videos that I made before, then I posted that to you, and I put a link back to that earlier on one. So if you look for the chat, you can see some of the answers that I've already done from that. So it's great to see you all chatting away and having a chat. So I'm going to kind of ignore the chat while I do the first little bit. But all the best for tomorrow. I'm sure you're going to do absolutely fine, and you got that rest for a week. And then at the end, I'm going to come back, dudes, and I will do a little Q&A session, and then I'll go through the prepared answers that I've done, the little bits of that, and then you can ask away. All right. If I can feel like I can do it justice, then I will explain something. If I can't really explain it and it's just going to confuse you, then I'll just leave it and try and point you into some good videos maybe afterwards in the chat. All right. So let's go into the kind of key explain answers that are going to come up tomorrow. Alright, so this is pretty much just got from a whole bunch of mark schemes. So I've just gone through them and I've picked out kind of things that come up time and time again. So polarization, for example, is where you've got to talk about vibrations being restricted to a single plane, and that plane's got to be perpendicular to the direction of propagation of light. Remember, sound can't be polarized because it's not transverse, it has to be transverse waves. Talk about this transmission axis and talk about the planes around that at right angles to it. Talk about proving that by using two filters, and talk about them being rotated by pi or 90 degrees difference to each other, so that they're that's polarized, and then it's 90 degrees. Talk about the intensity reducing as you rotate, and it'll be zero intensity when you've got odd multiples of pi over 2. Okay, hope that helps you with that one there. Talk about the transmission axis, which is the axis through the wave, okay, and the oscillations around that. So quantum is definitely going to be coming up, isn't it? Okay, always talk about electrons moving between energy levels. Talk about there only being, get this phrase in, there's only discrete energy level changes in atoms, okay. Talk about individual photons interacting with individual electrons. Get that into your answer there, okay. Remember, energy levels are discrete, and so there's only fixed energy level changes. There are only therefore a limited number of frequencies. There are only a certain number of energy level changes that are possible. Okay, now the previous one was about absorption and emission, so raising electrons up, falling down, emitting a photon as they do. Obviously, they absorb a photon, they raise up. As they fall down, they emit. And the photoelectric effect is similar but different. Okay, so this photoelectric effect is when you have a metal, it's got some stored charge on it, and you've got, again, one photon interacting with one electron. Look, talk about the photon energy being equal to HF. Thanks, Kieran, that's nice of you. And talk about the threshold frequency and the frequency of the photon, or talk about the energy of the photon greater than the work function, right? So don't please make sure that you don't compare the frequency of the photon with the work function, or the energy of the photon with the threshold frequency, because you've got to compare frequency and frequency, or energy and energy. So be careful with that one. Frequency greater than the threshold frequency, energy greater than the work function. Now, if you do have a higher intensity of light, then that's just more photons, you get more photoelectrons released, okay? More electrons per second. The wave nature of electrons is really important as well. They're probably going to give you an example of a behavior. It might be a particle, or it might be a wave behavior, or it might be both, and say the electrons do this, so what does it tell you? It tells you that they have wave properties, or maybe they have particle properties, or they have both. Standing waves, talk about superposition, talk about them interfering. So normally one wave is reflected back on itself and it interferes, it superposes. At nodes, they're in antiphase, okay, not just outer phase, they are in like pi outer phase, they're in antiphase. Talk about there's destructive interference, therefore at the antinode they're in phase, so there's constructive interference. An antinode, there's maximum amplitude, or a node, there's zero amplitude. So those are the key terms to be getting into these answers, guys. Standing waves continued. talking about applying that to sound waves, okay, talk about the phase difference. And remember, this is something people often get wrong, mix up phase difference and path difference. Remember, path difference is odd number of half wavelengths, then you're going to have pi out of phase and destructive interference therefore. Okay, so moving on to the kind of space stuff now. Doppler shift. Now Doppler shift, we describe it as a change in wavelength, okay, so when something's moving away, the wavelength appears greater. There's a change in observed wavelength because the relative motion of the source and the observer. Okay, if the frequency is moved, then it's moving towards. If the frequency is decreased, then it's moving away. So use those terms. Now, thermodynamics, thermal physics, just talk about energy being transferred from stores to another stores. Okay, this is a really important one for oscillations module. So defining SHM, it comes up time and time again. You can say the acceleration is proportional to displacement from an equilibrium position and towards. So I always write F equals minus K delta X. So it's the force is proportional to the displacement, that's delta X, and towards is the minus. So you can talk about the acceleration or you can talk about the force. If they ask you to define SHM, it's normally going to be using one of those. Well, it's definitely going to be that one of those two, either acceleration or force proportional to displacement towards the equilibrium position. Talked about trigonometric parallax in a previous live stream and done it loads, okay, but if they ask you to explain, you can use the diagram. That's in one of the live streams that I posted on the answers to the earlier live streams, so find that. But I'm sure you can memorize that diagram. Basically, if you have to explain it, you need to put it into words. We view these stars, and it's for closer stars, not distant stars. We use these stars. We view these stars two positions, 6 months apart. Okay, like opposite ends of the Earth's orbit. The change in angular position is measured. Okay, so it's not the angular position, it's the change in angular position relative to a fixed background of stars, and then we just use trigonometry with that angle. Okay, and that's where we get these units, the parsec and everything like that, which is just converting an angle into a distance. And we can do trigonometry because we know the distance from Earth to the Sun, so we know the radius of that orbit, and we know that we've gone halfway around that orbit, so we know the base of the triangle basically. And now standard candle is for more distant stars. A really easy answer. What is a standard candle? How can we use a standard candle method? Okay, it's an object of known luminosity, and I'm just going to move that out of the way because you can't see that word there. It's an object of known luminosity and measured brightness, okay? And then we use the inverse square law to work out the distance. So in this equation, the intensity is the brightness. That's like how, you know, what the power per meter squared is here on Earth, and the luminosity is the power actually output from the star. Okay, so those are the two things in this this law here. So it's really easy to answer that one. Okay, known luminosity, measured brightness, and inverse square law. How do we know the luminosity? Well, I'll come on to that later on, but it's basically by Wien's law. Gas pressure. Okay, talk about the kinetic energy of the molecules. Remember that kinetic energy is proportional to the average the average kinetic energy is proportional to the temperature. The collision rate of the walls of the container, you need to talk about that. How often they're colliding, you need to talk about the rate of change of momentum. Okay, so it's about the sum of all those forces against the walls of the containers. Those are the words you need to get into your answer. So, you know, this one is talking about smaller force because there's fewer collisions per second. Specific heat capacity, so this is specific latent heat rather. The temperature stays constant, okay, the internal energy is still increasing, so there's this tricky idea, isn't there, of internal energy being the sum of the potential energies and the kinetic energies of the particles, and when change of state, then the potential energy increases, the kinetic energy does not, so they get further apart. They're further apart in a electric field, okay, so they're attracted to each other by the electrostatic forces in between them, those weak intermolecular forces from your basic stuff, and they're further apart. Now, even though the force is smaller because they're further apart, there's a greater potential there, and so that's what's happening during the change of state. Okay, moving on. So Redshift and Hubble. So we're going to talk about Hubble again a bit later, but remember, Hubble just found that the further away, the greater the redshifts, therefore the faster they were moving, and that they were proportional. And therefore we get this Hubble constant, okay, which I'll talk about in a little while. Material behaviors is coming up in this next one, so elastic materials, and make sure you go over it and just look over your AS stuff, which is all pretty basic stuff now for you, but you need to make sure that it's slick and it's easy for you. So elastic material is something that returns to its original shape when the deforming force is removed. But plastic deformation is a permanent deformation. Again, once a force is removed, it still stays that same new shape. Resonance, spot the resonance question, because if you spot the resonance question, it's going to be, what's the name of this blooming thing that's going on here? Resonance is occurring, is worth a mark. If you can spot that the resonance is occurring, it's worth a mark. When the driving frequency matches the natural frequency, that's what you need to get into your answer. Driving frequency equals natural frequency. There's a maximum energy transfer, so therefore the amplitude rapidly increases. Those are the words that you're going to get into your resonance answer to make sure you are getting full marks on that bit there. Okay, that's a really easy kind of 3 or 4 mark question they're going to ask you about resonance. Damping is when they're taking energy out of the system. So energy is being removed from the system by some form of damping, okay, something connected to it, or a spring oscillator, or anything to remove energy from the system is a way of damping it. You haven't changed the frequency, but you've damped it, you've taken energy out, so therefore it's dissipated that energy, and therefore the amplitude of the oscillation is kept small. Try and get these words in, try and memorize this way of explaining it using these key terms. Stellar evolution, somebody asked a really good question, I think. How much detail do we need to give in our answers about stellar evolution? So, this one is just a section of it, but it gives you a kind of flavour of the detail you need to get into the answer. The problem is that when we talk about stellar evolution, most of the time we get excited and we start talking about all these amazing things about stars, but what details do you need in your answers? Okay, let's do this. So, in the main sequence, we've got hydrogen to helium. So we want to talk about, during the main sequence, hydrogen is being converted to helium. We've got fusion going on. During the main sequence, there's a constant luminosity. There's also this balance of forces, the radiation pressure outwards and the gravity force inwards. Okay, so but during the main sequence, there's a constant luminosity. Remember, we talked about where do we know that luminosity from in the standard candle? Well, it's because we understand all these stars fit on this main sequence on the Hertzsprung-Russell diagram, which I've got a little chat about in a minute as well. So once the hydrogen in the core is depleted, you get less hydrogen fusion going on, or no more, and the star actually collapses inwards a little bit, okay, and the temperature increases, and now helium fusion occurs, right? And then, because there's more fusion going on, then it expands again, and it cools, okay? So they get this kind of feedback loop, and actually you get this pulsation, and that's how we can measure, what's going on with those stars and whether they're likely to do supernovas. See, we get excited and we start talking about extra detail, but what you need to say is it expands and cools and forms a red giant. Okay, so that's the level of detail you need. And then eventually, if it's a red giant, if it's not big enough to be a supergiant, then the layers disperse and the fusion ceases, runs out, but it's still pretty high temperature because it actually, the core is a very high temperature, so it's white, so it gives out, and I'll talk about radiation curves, Wien's law curves in a minute as well. It's white, so that's how you need to know that. So just try and get this level of detail in. Go through your book again and just try and think, all right, this, what is the level of detail that I need? I think that's a good one to go through. Somebody asked about ray diagrams as well, and I'm not going to draw them out again because I've done that, and I've posted some example answers there. So ray diagrams, remember to always do the ray parallel firstly to the principal axis, then through the principal focus. Okay, so from the middle of the lens through the principal focus, and then also one right through the very optical center of the lens, and lastly where they cross is the top of the image that's been made. Okay, that is all the chat from there. I'm gonna have a quick look at the chat, see how much you guys were listening. You're gonna have to excuse my face here because well, you'll see. This is the this is the kind of chat box. This is the webcam thing, so I can have the green screen behind me, but it's not working great, I must admit. But how's it going? Any good questions in here at the minute? Lots of people talking about the last paper still. I would not be worrying right now about the last paper. I'd be worried about the next one. Yeah, luminosity and temperature graph is coming right up now. That's the Hertzsprung-Russell diagram. Was that useful? Tell me if that was useful or not so much. Yeah. forget the last paper now, it's done. Of course there are girls here. Yeah, the flower question was a bit mad, but I looked at it myself, and actually you can solve it, guys. You know, you gotta take your time over these questions that are a bit iffy, they're a bit weird, like, well, what on earth is going on? You've got to take your time, and you've got to think, what do I know that can solve this? And actually, that flower question was just a bunch of blooming equipotentials. All right, it was actually possible to do that. I know, it's a wiggy kind of blooming context, but where can you pick up the marks, right? Yes, my real name is Sir Gorilla, absolutely. Let's stay focused, people are saying, yeah. Okay, I'll come back and you can ask me some serious questions after I've just done the little bit of space stuff that people asked. Thanks again, Kieran, that's very nice of you. Yep, nuclear physics is coming up tomorrow as well. Angus is pining away for Sophie. Forget Sophie for a minute, right? She'll be impressed when you get your grade in your A-level. Okay, right, yeah, it's the most useful stuff. You can have fusion on Earth, but the issue is that it's going to melt any of the containment, but also it's going to deposit its energy. It's going to heat up its containment, and so it's going to lower its temperature, lower the plasma temperature, and its fusion is going to be harder to maintain on Earth. So what we need to be doing really on Earth, I think, is just use this massive ball of hydrogen that we've got fusing out there in space, the sun, and just get the energy from that. I know the exposure's way crazy, but it looks good on the PowerPoint mode as well. All right, gonna leave it. Gonna go and talk to you about some space things now. So gonna go into the, yeah, go on, Angus. Gonna go into the visualizer now. Okay. I do really want to sort out this exposure, so just give me 30 seconds. Okay, so there we go. So this is a Hertzsprung-Russell diagram. Okay, and they're pretty easy. Now, one reason I wanted to go through this is somebody asked about reading a log scale, and they said they think they messed up the log scale question in the paper, the last paper. That means there's unlikely to be like a directly just reading off a log scale kind of question in the next paper, paper 2. But Hertzsprung-Russell diagram is an example of a graph that's got log scales on it, and you need to be able to read off them kind of roughly from the Hertzsprung-Russell diagram. So this strip down the middle, this is the main sequence. Here you have the brightest stars, and here you have the dullest stars, and here you have the hottest stars. Okay, and remember this temperature axis is backwards. Okay, so here you have the hottest stars, and here you have the coolest stars. The luminosity axis is given as a ratio of the luminosity of the Earth. So 1, not the Earth, sorry, the Sun, our Sun. 1 is the luminosity of the Sun. So our Sun is here on the main sequence. Okay, so you need to be able to find that. Up here, these are the red giants, and these are the red supergiants. Now, during the star's life cycle, they're going to just be promoted off the main sequence up into these giants regions. Depending on how much hydrogen they've got, this is going to determine their ultimate fate. So we talked about the drifting off into space. These are the ones that are going to go supernova, and once they've gone supernova, they're no longer on the HR diagram. Our star is going to, once its outer layers drift off into space, will come down here into the dwarfs section. So these are the white dwarfs. Notice they're hotter. Okay, they're a higher temperature, even though they've got less energy. Okay, I hope that helps. Now, the point is to understand your scales. Don't forget that this is the highest temperature, this is the lowest, so this temperature axis is backwards, and this is the luminosity, the radius of the luminosity of the Sun, and it's a log scale. So if you look at this number here, this is 1, so this is equal to the luminosity of the Sun, and this next pip on it is 10 to the 2, so this is 100 times the luminosity of the Sun, and this next pip up here is 10,000 times the luminosity of the Sun. So what is halfway between this and this? Well, halfway between this is 10. Okay, so it's not a linear scale because it goes 1, 10, 100, 1,000, 10,000. So actually reading in between these is pretty tricky. So I've just gone ahead and made a little kind of sketch of in between. We've kind of zoomed in on this little section here, if you like. Okay, so this is 10 to the 1 and this is 10 to the 2. So this is 10 and this is actually 100. Well, what's halfway between that is going to be 2 times 10 to the 1. And then a little bit higher up is going to be 3 times 10 to the 1, 4 times 10 to the 1, 5 times 10 to the 1, 6 times 7, 8, 9 times 10 to the 1, and finally 100, okay, or 1 times 10 to the 2. So you have to be able to kind of quite accurately get from a Hertzsprung-Russell diagram and read off these pips here. So this would be 2 times 10 to the 0, which was just 2. Okay, so I hope that helps. But again, so we're talking about these temperatures. Why is it these stars have different temperatures? And somebody asked a really good question about, why do stars give out a certain spectrum? Okay, so let's talk about that. This, if you like, is the color of the stars, and these are the reddest stars, the coolest stars, and these are the bluest stars. So they have these spectrums, and it's not because they only give out red light or only give out blue light. They actually give out all different colors of light because they're an incredibly hot mass of gas, and they're giving out all different temperatures at all kind of times. But we know what they are by what we call the peak wavelength. So the peak wavelength is this on the Wien's law curve or Blackbody curves. Okay, so this star is a hotter star because it has a greater intensity around this wavelength, which is a bluer end of the spectrum. Okay, so this is this on our Hertzsprung-Russell diagram would be a bluer star. Okay, it would be a higher temperature star. It's going to be one of the more massive stars that's going to go ahead and make a red supergiant probably and go supernova. This would be a red one, okay, which has a lower peak wavelength. And we use our peak wavelength in Wien's law, which is this, that just says peak wavelength is inversely proportional to the temperature, and it's inversely proportional to the temperature, and this is the constant that it equals, is this number meters Kelvin. So wavelength times temperature is going to have a unit meters Kelvin. So this allows you always to work out the temperature of the star from lambda max. Okay, and that can then be used in Stefan's law, etc., to give you the relate the surface area to the luminosity. I'll show you that equation. Stefan's law just here. Okay, relates the surface area of the star, that's the A there, to the temperature and to the luminosity, and this is just the Stefan-Boltzmann constant that's given in the equation sheet. Alright, so I hope that helps. That's how we get to work out the luminosity for our standard candle as well. Okay, and the next thing is just think about it like this. Stars, as I say, are these really hot balls of gas. Okay, now you can use, and you should use, your quantum knowledge to explain why it is that they're hotter, so release these spectrums that have peaks around the higher, or have peaks at different wavelengths, right? So hotter ones have peaks at shorter wavelengths, bluer light, higher frequency, higher energy light, and that's because you've got more photons of a higher energy being released, because you've got more movements of electrons between higher energy level changes. So within that massively hot ball of gas, you've got more movement of electrons up and down between those higher energy level changes, so you're giving out more higher energy photons. Okay, so you use your quantum to explain where this spectrum is from. Now you also, from each star, get these absorption spectrums. Because it's a ball, remember, of hot gas, it's not only giving out these photons, but it's also emitting these photons. Okay, so you get these spectrums which have these dark lines on, which are the absorption, the absorbed wavelengths, the absorbed frequencies of light. And again, it's the same kind of quantum argument. We're talking about electrons moving up to high energy levels. We're talking about that light being emitted from within that ball of gas and traveling out through the ball of gas. So it's absorbing all the wavelengths of light as it goes as well. It's absorbing these discrete frequencies, these discrete, corresponding to those discrete energy level changes. I hope I'm saying that often enough that you're going to get them into your answers tomorrow. So electrons are moving up to high energy levels. Again, one electron is absorbing one photon by moving up the energy levels, discrete energy level changes, and talking about the energy of the photons being proportional to the frequency. Okay, so that's where those spectrums for stars are from. And then Hubble's law and the ultimate fate of the universe. Hubble's law is just this proportionality between the speed things are going away from us and their distance from us. So Hubble used, he measured the radii of the angular diameter of galaxies, and just presumed they were all roughly the same size, and the angular diameter therefore gives you an idea of the distance. And he measured the recessional velocity, hopefully you know that, by Redshift. And if you plot that graph, you get a gradient h0, and h0 has units, seconds to the -1, or time to the -1. And that number is inverse the age of the universe if the whole universe was expanding at the same constant rate. And that's where this controversy comes in. And somebody asked about the spec point on Edexcel, which says understand there is controversy around the ultimate fate of the universe. When we measure h0, we get quite large uncertainties, we get quite large discrepancies. So what we have is a kind of average over a large number of different readings. And that averages out to being the age of the universe being 13.7 billion years, right? But we're not absolutely sure about that. We're not certain about that. Recent measurements have changed that kind of thinking. So this is the ultimate fate of the universe. This is just a graph of kind of, the distance between galaxies. So you can see this y-axis of kind of being like the size of the universe, and this is time, and this is where we're up to now. This is time 0, and back here is minus 14 billion years, and this might be 14 billion years in the future. Okay, in times 10 to the 9 years. Now, we don't know. Now, when I was your age and I was studying A-level physics, this graph here, this closed universe, this seemed pretty convincing. And this was if the density of the universe was greater than a kind of critical density, right? So what would happen, therefore, if it was greater than the critical density, is that the universe would kind of collapse in on itself. It would be so attracted by all that gravity, because it's so dense, that we would have this situation where the universe would reach a certain point and then start moving in on itself, being attracted to everything else by gravity, and the universe would collapse. We'd have a big crunch. And actually what we kind of were surmising, what we were guessing at, would be that then you'd have another big bang and then the whole universe would start again, right? So that was pretty convincing. I was pretty happy with that. I was like, wow, that makes perfect sense. That's what's going to happen. We're just kind of one of a whole series of different universes, just expanding and then collapsing, expanding and collapsing over time. But evidence has changed now. Now the other options would be a flat universe, and that's this kind of heat death, this kind of, everything tends toward entropy. Universe just spreads out and then stops at a certain temperature, and boom, we're kind of done. And that's if the universe's density would be equal to the critical density. Or the universe could keep on expanding forever, maybe at a constant rate, maybe at a declining rate, but generally it would expand forever, ever. And that would be if the critical density was less than 1. Now, here we go. This is the issue. What we're finding now from standard candles of quasars in distant galaxies is actually the universe appears to be accelerating. It appears to be getting faster, and that's this controversy. And all you really need to know at this point, okay, for your A level, is that we think that's because of dark energy. It's like, well, if there's an acceleration by Newton's second law, there must be a force pushing out. So you know what's going on, therefore there must be some energy that's actually accelerating the universe. And with the evidence, more and more evidence, different experiments are being conducted, and more of a reproducible finding that actually the universe is accelerating. So this is probably the answer, and that's why the riddle at the minute in physics is dark matter and dark energy. All right, that's that really. That's all I've sort of planned to say. There's a couple of other questions, and people are being very useful here. with some very, very interesting letters there, but there was an interesting question. Yeah, I'm gonna drop the feed pretty soon. There was one interesting question. Magnification lenses, when is it positive and when is it negative? How do you know to draw converging or diverging? Right, I'll do this for you then, my buddy. Yeah, you definitely need to go and eat pretty shit soon, so let's do this. Any other kind of questions? Yeah, I like these t-shirts as well. I think I need to get sponsored by Levi's. Okay, so let's do the ray diagrams one more time for posterity on ray diagrams. Why not? So basically, I think the difficulty with people understanding ray diagrams is when to use each type of lens. That's terrible. Let's use these lines then. When to use each type of lens and when to use the different focal points. So if you have a diverging lens, then it looks like this. The object is over here. This is the focal points. We use this focal point here. Now the power of a diverging lens is negative. So let's say power is equal to -1 over f, right? Or you could say, well, the power is something in negative diopters. Okay, this is the focal length here. So the focal length you actually use is this one here. So when you're doing the ray diagrams, always do this line, no matter what the lens is. Always do this line through the optical center of the lens. But because it's a diverging lens, it's going to go out. It's going to put the light outwards, so you use this one. So now the light didn't really come from here, so we do it dotted because it's an imaginary ray, so therefore it's a virtual image. The top of the image is formed where the two rays cross. So the eye sees these two rays and sees all the other rays coming from this thing incidentally as well, but it sees these two rays and it interprets them as if they're coming from here. And if you're using a converging lens, same exact diagram, except now we're interested in this focal point, the one on this side, the far side of the lens. Same start, get a mark. Same ray all the way through the center, get a mark, and then use this one here. Again, where they cross is where the image is, or the top of the image is. And so this is a real image. Now the test of whether it's a real image is basically if I put a screen where the image is, does that image get projected on the screen? If I put a screen where this image is, does that image get projected on it? No, in fact what it does is it just blocks out the light, doesn't it? Okay, so I hope that makes sense really. That is when you use converging lenses, use this focal point. So with a convergent lens, or in this case V is positive, whereas with this situation, divergent lens, if it's over on this side, basically V is negative. It's a bit like a graph, right? It's a bit like a graph with the lens being in the middle. If I draw a graph, this way is positive and this way is negative. So if your measurements that you're using the focal length on this side, well, that's a negative focal length. If V is on this side, well, that's a positive V. Okay, hope that makes sense, dudes. All right, anything else, guys, in the chat? Or is that it? I think you guys need to get yourself a good night's sleep. If you're on Ramadan, then have a good iftar with all your family and friends. That's awesome. Yeah, I would suggest have a chilled out rest of your night, get to bed within an hour or something, make sure you're ready and in good nick at 9 o'clock in the morning. Take your time, possibly go over some past questions, maybe watch through my exam playlist, paper 2 exam playlist, maybe look back at that previous live feed I did earlier on with those questions, and where I've got a good question where I've got a good video to explain something that people have asked, then I've stuck a video on that into the chat like that. If you've got, he's a fan of mine. All right, hi Craig. Yeah, I'm a fan of physics teachers everywhere, Craig. So give me a shout. Give me a shout, Craig. Give me a shout and we'll chat. Or get me on kit@gorillaphysics.com if you're a fan, Craig. Okay. I don't do predictions because literally anything can come up. Glad that was helpful. Some people's just saying thank you. That's great. Am I role playing a red giant? Is that because of the overexposed part there? Yep. Nice one. Oh, nuclear energy graph, nuclear binding energy graph. Should we do that quickly? What was it? Nuclear binding energy. What was the other one? Electron diffraction. Okay, go on then. Back into the visualizer. Nuclear binding energy. Then this graph. This is going to be a terrible sketch of it probably, but remember this is the average binding energy. Okay, and this is the nucleon number, or the atomic number, it could be as well. Okay, now you've got this curve like this. Okay, now essentially the binding energy is the energy released when the nuclear interaction happens, when the nuclear decay happens. So these ones here are the fusionable elements, because by joining them together, you release energy to come up here to the higher average binding energy per nucleon. Now, get away from thinking about that as being the energy that's holding the thing together. Think about that as being the energy that is released when the nuclear decay happens. So, and it just so happens that helium is an oddly high spike on this curve. Helium is just here. So alpha particles are incredibly tightly bound, incredibly stable arrangements of particles. Now so is iron 56, and iron 56 is the most stable arrangement of particles, and that's why everything heavier than iron 56 was made in a supernova, because you have to put in extra energy in to make these. So this way on the graph is the fusion, where you get energy out by smaller nuclei joining to make larger ones. On this graph, this is the fissionable side, okay, where large elements split to form two smaller elements, okay, and that releases energy. So this is the fission side, because the average binding energy per nucleon goes up, so it's a more stable situation. Remember, the whole universe is just tending towards stability. Everything, there's a probability of any point of anything decaying to become more stable than it is. Okay, so if it's moving this way, it actually gives out energy by fission. Okay, I hope that helps. What was the next one somebody asked? Oh yeah, about electron diffraction. Electron diffraction is just like any other diffraction really. It's just that electrons have a wavelength called a de Broglie wavelength. So just chat that through, just find the equation for that. I know it, right, but I always check, because who wants to get things wrong? Okay, lambda equals h over p. That's the Broglie wavelength, okay, which says that the higher the momentum, the smaller the wavelength, and h is Planck's constant, which is given to you, which is a constant, yeah. So basically, most of the time this will be about some form of accelerating an electron, probably through a gap. So we normally have a fermionic emission, like very high voltage. Okay, so like EHT, somewhere in the region of kilovolts. So we basically get a filament really hot, and that releases electrons, and then we attract that to a charged plate. So this is the anode, very highly positive. So there's 1,000 or so, order of thousands of volts, 5 kilovolt supply between here and here. You get the electron, you accelerate it through that potential difference, so it's accelerated to here. It is now an electron with 5 kilo electron volts of kinetic energy, okay, which you can convert into joules if you like. So the next step in, a typical question of this would be convert non-SI into SI, so you've got joules, then use kinetic energy is half mv squared to work out the speed of the electron. And you obviously get given the mass of the electron in the formula sheet as well. And from that, then you can work out there's the mass of the electron just in here, look. Okay. From that, you can then work out the momentum, and hence you can work out the wavelength. And basically the electrons are going to be, things are diffracted, waves are diffracted when they go through gaps which are roughly equal to their wavelength. So the electron actually behaves like a wave and diffracts when it goes through a gap roughly equal to its de Broglie wavelength. Okay, it's a wave behavior of an electron, hence the wave particle duality. And if you increase that voltage, then you increase the momentum, so you decrease the wavelength, and so you get tighter interference patterns. So it actually is exactly the same as the laser interference patterns that you'd have done, or the Young's double slit stuff, which is this equation here. N lambda equals d sine theta. So higher momentum, I'll just have to write the Broglie wavelength down here as well. So higher momentum, smaller wavelength, so smaller wavelength therefore in this equation, so smaller value of sine theta, where d is the gap size. So when you've got double slit interference, you've got it coming from now like 2 gaps or multiple gaps because it's diffracting off like atoms in a crystal. This interference pattern that's produced here is going to have a smaller angle between each maximum. Okay, so you're going to have a tighter, smaller gap between the maximums on your interference pattern. I am gonna go have a little chill now. Look over some things, but don't stress it. Think through. A good thing to do is like go through your equation sheet and actually go through and think, right, when am I going to use each of these equations? Double check that you know what all the terms are, everything like that. I'll be back for core practical paper 3. You can already have a little look after this one for core practicals. All the core practicals in Edexcel is a good video. It's my most popular video at the minute. It's a really good one to be looking over. You do need to kind of have some awareness of that, but most of them will come up in the paper 3. Now Caitlin's just asked for the long, oh no, not okay, and Ansha's just asked for the long derivation in thermodynamics, please. I did that in a recent live feed, so if you ask in the comments, any questions in the actual comments, I will put any videos I have for that. So Anisha, just do me a favor, just ask for that in the actual comments of this video once I've dropped this feed, and I will put a video where I've gone through the long derivation. I know the exact one you mean. It's my least favorite derivation in all of physics, so I'm not going to do it live just now. Yeah, I'm glad, Imam. Yeah, like the stream please as well, it'd be really, really useful just to get it a bit more popularity. Alright, awesome. Do things as well, go back to the start, why not? And watch that those common explain answers again. Get that language ready to go in that exam. Alright, I'm glad, dudes. Off I go. See you later. You don't need luck. You've worked hard at this for years. Okay, you're ready for this exam tomorrow. Just go in there, apply the different parts of it to those questions, to those tricky things. When they give you the gravitational field around the sunflower, as somebody's pointed out earlier on, just treat it like any other gravity fields question. You can do it. All right, cheers now.